We have synthesized the topology of the current controlled voltage source using a MOS transistor. Now we will analyze it to see exactly how it behaves. We have the input current source II, and we have the MOS transistor here, gate, drain, and source. Okay, and we have to connect the resistance which represents the trans resistance. That is, we want V0 to be equal to II times Rm. So the output V0 is over there. Okay, this is VGS and this is GM times VGS. Now, in addition to this, our current source may not be perfect, so it has a resistance Rs across it, and of course there will be a load because we want to be driving something. This is the complete circuit. Okay, and you can now analyze what really is V0 by II in this circuit. Okay, as usual, I would encourage you to carry out the linear circuit analysis and find the transfer function. Okay, and then you can compare it to what I get here. Now, this particular circuit, it turns out that we have analyzed this before in a somewhat different form. Okay, so if you remember long back, we realized a common source amplifier using drain feedback bias. Okay, if you recall, the small signal equivalent circuit of that was like this. The MOS transistor was here, the input was a voltage source Vi in series with a resistance Rs, and the feedback resistance, it was called Rg. This is VGS and GM VGS, and this is RL. Okay, now you can see that what I have here looks exactly the same as this. What is Rg here is denoted by Rm over there, and instead of a voltage source in series with a resistance Rs, I have a current source II in parallel with a resistance Rs. So all the results that I obtained here can be used here. Okay, now we can go and analyze this from scratch. In fact, as I suggested, please do that and make sure that the answer that you get are exactly the same as what I get. Now, one of the reasons I am connecting it to this is just to be able to use results from a previous analysis, which sometimes you can do, and also to illustrate how the same circuit can behave quite differently when component values change. Okay, because this, as I said, it's a common source amplifier, and this one is a current controlled voltage source. Obviously, it behaves as a common source amplifier for some combination of values and a current controlled voltage source for some other combination of component values. Okay, we'll see all of those things. Now, how do I relate these two? This part here, Vi and Rs, is the same as that part. Okay, these two will be exactly identical to each other if Vi equals minus II times Rs. What I mean is, this current source in parallel with Rs will be the Norton equivalent of this voltage source in series with Rs if Vi equals minus II Rs. We get minus II because this current source is pointing downwards, whereas this voltage source has positive terminal on top. Okay, now with this mapping, we can use whatever results we have for this circuit for our current controlled voltage source. The only other thing we need to do is wherever we have Rg, we have to replace that with Rm. That's a trivial modification. Okay, for the common source amplifier with drain feedback bias, we had V0 by Vi to be minus GM RG RL minus RL, okay, divided by GM RL RS plus RS plus RG plus RL, okay. Now exactly the same thing works for us, except I have to replace this VI with minus II RS. So if I do that, I get V naught by minus II RS to be equal to that, and I want only V naught by II. So I multiply this with minus RS, okay. So V naught by II will be equal to GM, RG is called RM, RM RL minus RL times RS divided by GM RL RS plus RS plus RM plus RL, okay. Now what is it that we wanted? We wanted V naught by II to be equal to RM, okay. Now will this expression ever equal that one? It looks like that. Let's say if this term happens to be dominant in the denominator, okay, let's say this is the only term that is dominant in the denominator, and of course this dominates over that. That's not difficult because this GM times RM can be quite a bit larger than 1, so this will dominate over that. If GM RM is much more than 1 and GM RL RS is much more than RS RM and RL, in this case clearly you can see that this approximately equals RM, okay, under these conditions. So what we synthesized as a current controlled voltage source using our intuitive idea of negative feedback does behave like that. The exact ratio of output voltage to input current is not RM, but some value like this, but it will be very close to RM, okay. In fact, if these conditions are satisfied, it will be close to RM, okay. So when you choose the component values, you have to make sure that these conditions are satisfied, okay. So this is the expression for V naught by II. We will simplify it in different ways and see what comes out of it, okay. So first of all, if it is driven with an ideal current source, that is RS equals infinity, then what happens? I have to evaluate this expression in the limit RS tending to infinity, okay. It's very easy to do. I divide both numerator and denominator by RS. I will get GM RM RL minus RL divided by GM RL plus 1 plus RM plus RL divided by RS. Obviously, as RS tends to infinity, this goes away, and I'll have GM RM RL minus RL divided by GM RL plus 1. What I'll do is I'll divide all the terms by GM RL. So in that case, I'll get RM minus 1 by GM divided by 1 plus 1 by GM RL, okay. So this is the expression if RS is infinity, that is if the current controlled voltage source is driven by an ideal current source, okay. Now what is this saying? If GM is very large, okay, that is basically if GM RM is much more than 1, then this term in the numerator will be much smaller than this and can be neglected, okay. And similarly, if GM RL is much more than 1, then this entire thing approximates to RM, okay. So essentially, just like in all the other cases in the negative feedback amplifier, just like in all the other control sources, the GM of the transistor, the transconductance of the transistor has to be very large. If it is very large, in fact, if it tends to infinity, we will get exactly the relationship that we want. Okay. For instance, here you can see that if Gm tends to infinity, you will get Rm exactly. Okay. So that's what happens in every case. Okay. If Gm tends to infinity here also, you can see that you will get only Rm. Right. Now, if Gm is finite, it will slightly deviate from Rm. This was the case for all the other control sources as well. There was some small difference. We wanted a voltage controlled voltage source with a unity gain for the source follower, but you know that the source follower's gain is close to 1 but not exactly 1. It will be equal to 1 if Gm is infinite. Okay. So as Rs tends to infinity, you get this. Okay. So let's look at these two expressions. This is the gain or ratio of output voltage to input current for the current controlled voltage source, and this was the gain of the common source amplifier with drain feedback bias. Okay. So in this case, we want this particular term to be dominant one. If that is dominant, then we get approximately what we want. V naught by I approximately equals Rm. Whereas in the common source amplifier with drain feedback, if you recall, we wanted this to be dominant. Okay, Rg to be dominant in the denominator. So if this is dominant, then we have V naught by Vi approximately minus Gm RL. Okay, so they are quite different. They are quite different from each other. Now you can see that the only difference is in the values of the components. If you choose the value such that this Rg is dominant over all these terms, it behaves like a common source amplifier with drain feedback. And if you choose value so that this is dominant, the term containing Gm is dominant, then it behaves like a current controlled voltage source. Okay. So this also emphasizes that you have to understand what is going on in the circuit. Okay. Exactly the same circuit. They look exactly the same. The topology is exactly the same, but the behavior is very different depending on the values of components. Okay.